Let's talk about Taylor's formula, one of the most important things of calculus. And we're doing calculus 1 here, so Taylor's formula in dimension 1. So the introduction is, if we start from the definition of the derivative, so if f is differentiable at the point A, then this limit here is equal to the number f primed of A, the derivative of f at A. So, and this means that for x near A, this quotient f of x minus f of A over x minus A must be approximately equal to the derivative of f at A, because this is just what the limit means, right? So for all x sufficiently close to A, this quotient is approximately this number, right? This is what it means for f to be differentiable at A. And so here you can multiply both sides with the denominator, and you get this. And if you move this number over to the other side, you have f of x approximately equal to f of A plus f primed of A times x minus A for x close to A. And this is the formula for linear approximation. And this is basically that you can, one thing to express this graphically is that you can approximate the graph of the function f with a tangent, like in this picture here. The white curve here is the function graph of f, y equals fx. And the yellow line here is the tangent to that curve at the point where the x coordinate is A. And so for x close to A here, you can approximate the white graph with the yellow tangent. And so this is first order approximation. You approximate with a first order polynomial, because the right hand side here is a first order polynomial, a first degree polynomial of degree 1. And so let's call this P1 of x, the right hand side. Let's call it P1 of x. And this is a polynomial of degree 1 that approximates the function f near the point A. And specifically at the very point A, the value of the polynomial is exactly the value of the function, because if you plug in A instead of x here, you get f of A is equal to the right hand side where you plug in A instead of x, and you get f of A here, right? So this polynomial matches the value of f at the point A. And if you differentiate this polynomial on the right-hand side, then this one vanishes, the parenthesis vanishes, it's 1. The derivative of the parenthesis here is 1. So you get the derivative of f at A. So this polynomial P1 of x also mimics the derivative of f at A. So one might wonder if you can do even better. Can you match also the second derivative of f at A and get an even better approximation? So the question is there a polynomial P2 of x such that it matches the function value of f at A, it matches the derivative of f at A, and it also matches the second derivative of f at A? Is there such a polynomial? Well, since we want to keep these properties of the first order polynomial, why not start from the first order polynomial P1 and add an extra term that also gives us this last condition? So let's try something like this. Let's try P2 of x equal to, here's P1, right? F of A plus f primed of A times x minus A plus some number times x minus A squared. And we're hoping that we could sort of choose this number k in order for the second derivative to be matched as well. So if this is our polynomial P2, it's clear that these two conditions are already met. The first two conditions are already met. Because if you plug in a instead of x here, you get f of a, right? And if you differentiate once and this disappears, this is just f prime of a, and this one is k times 2 times x minus a, and if you plug in a instead of x, this is 0. So for this polynomial, no matter how you choose the constant k, the first two conditions are met. So how should we choose k in order to get this last condition fulfilled as well? Well, let's try and differentiate this polynomial twice. If we differentiate this polynomial twice, then this disappears and this disappears, and we get 2k here. And we want 2k then to be equal to the second derivative of f at a. But this tells us that we should choose k to be the number second derivative of f at a over 2. Right? So if we choose k like this, then we get a second degree polynomial that has these properties. Correct function value, correct derivative, correct second derivative at a. And we can use that polynomial to approximate f at points close to a. And as you know, greed has no limits. So it's obvious that we would want to continue here and construct a third degree polynomial that is even better, and a fourth degree polynomial, and so on. And we can continue this process in the same manner. And if we do it n times, we get a polynomial of degree n that is constructed this way. We start out with f of a, and then this is the first order term, and there is a second order term that we determine, and we keep going here. And after n steps, we add a term, which is the nth derivative of f at a over n factorial times x minus a to the power n. And this polynomial Pn of x, it matches the function value and the derivatives of f up to order n at the point a. Just one note about these factorials. Here we divided by 2, and here there's a 2 factorial, which means 2 times 1, and it's equal to 2, so it doesn't really matter in that case. But if we continue and have a third degree term here, then if you differentiate that, in the first step you get a 3, second step you get a 2. So if you differentiate x minus a cubed, if you differentiate that 3 times, you get 3 factorial, 3 times 2 times 1. And similarly for the higher powers. So this is why you really need factorials here. Here it doesn't really matter. You can write just 2 or 2 factorial. They're the same. But from the third term here on, you really need the factorials to make it work. Right. And then you might wonder if you use this polynomial to approximate your function f at points x close to a, what is the error you make? Because you probably will make some kind of error. And there's a formula for the error. The error term is by definition the difference between f of x and Pn of x. So this is the error in the approximation. And the thing about this is that the error term, it looks like the next term in this series would look like. So you need an n plus first derivative of f, you need an n plus 1 factorial here, and you need a power n plus 1 here. Right? So this is the error term here. There's only one thing that is sort of different, and it's this point here that you plug into your n plus first derivative. It's not the point a. Here is the point a. your base point, so to speak. So to get the error correct, you need to take this derivative at some point C between a and x. And you don't know exactly which one. But for some point C between a and x, the error in the approximation is precisely this. So that was a few words about the Taylor theorem. Thanks for watching.